Okay, hi everybody. Let's just take a quick
Good
look. Oh,
morning.
someone's in the waiting room. They're joining. Quick look at chat. Okay, good morning. Yes, I do need to. I need to post video from yesterday. So yesterday we did two things. If I summarize, what did we do yesterday? We did the proof of the Pythagorean theorem from Euclid's Elements, and we did the construction of the regular pentagon, also from Euclid's Elements, and that introduced the concept of the golden ratio. Today we finish Greek math. Let me just close this window because there's some lawnmower out there. Okay, now today is a really ambitious day, and we'll just see. Well, Greek math, regardless of how much I get through, that will be the end of Greek math. I'm hoping to get through all the material for today. I actually made a fairly extensive. If you go here, assignment 11. I have the code over here, Desmos code for today. Whoops.
Excuse me, Professor.
Yes.
Marcus is in the waiting room.
Oh, well, what's funny is that tell him if you're communicating with him is that it just says joining. I clicked admit. I clicked admit for him, but it's sort of hanging at the next step. So I'm not sure.
All right.
I'm not sure what to do. I think either to tell him I did let him in, but he's not being let in for some other reason.
All right. I'll let him know. Thank you.
R88B59 looks like the oh, here we go. Wait, someone else is trying to come in. So like I said, we have an extensive Desmos deck for today. Let's bring it up. And I'll paste the code here. Let's see. So it's R88B59, which I am going to post here. Into the chat. Yeah, Marcus is still, if you could tell him that it's saying, oh, I think he made it. Marcus, did you make it in? Or did you is Marcus here?
Yeah, he's here.
Okay, great. Okay, so here's the code for today's. It's R88B59. And like I said, today will be pretty extensive, but maybe I don't get through it all. There's no history of math. I've been studying it for 30 years. So of course, there'll be plenty of stuff that gets left out, and whether I accomplish 8 out of 8 things I wanted to do today or 5 out of 8, it won't matter so much. Today though is about one of the kind of more, you'd almost think I'm making this up. There's something in math called the 3 problems of antiquity. And they have different names. Some people call them the 3 geometric construction, the 3 construction problems of ancient Greece, different ways of saying it. But at least among math people, when you say the three problems of antiquity, those can only be the three things that I'm going to talk about today. And in doing that, we will be introduced to Archimedes. Archimedes is widely thought to be maybe the greatest mathematician who ever lived. So we definitely want to be seeing what he did. Archimedes is kind of a household name for his physics, law of buoyancy. I guess the king wanted to know if a crown that was made for him, because Archimedes was also applied scientist, was the crown really made of gold, or was it mixed with some kind of other alloy? And in the bath, Archimedes realized that, I don't know how you realize this in the bath, that if he puts equal amounts of gold that the crown should be into water, it should displace the same amount. And if it has some other alloy mixed in, it will displace water a different amount. I don't know how that would be at all obvious of a chemistry property. And then he ran through the streets nude, saying Eureka. So Eureka is a pretty famous word in Greek, and then people say it just in English, Eureka, I have found it. So Archimedes was known for being very eccentric, known for getting lost in thought, and working on a problem, walking through the street and thinking about something, and then needing to just stop and think, and just standing there for 5-6 hours, just kind of like statue as he thought about stuff. Archimedes was a mechanical engineer, and he invented a lot of mechanical inventions, including a lot of wartime inventions. And he was from Syracuse, and his war contraptions, which included some kind of claw that can rip apart ships, and just very catapults, things like that, pulleys. Some people say that he had mirrors that would burn things at a distance. So as the story goes, death of Archimedes, they were getting attacked by someone, I forget, Romans or something, and at that time, if people were climbing up a wall to attack Syracuse, all the Syracuse soldiers would have to do is throw a piece of rope over the end. It wasn't even a contraption, but everyone would think it's an Archimedes contraption about to kill them, and they would go running. Anyway, they finally breached Syracuse, and the soldiers were told, capture Archimedes, but don't kill Archimedes. He was 75 years old at the time, which is pretty old. And as the story goes, he was in his house working on some geometry. They did it on a sand, a board that had sand on it instead of a blackboard. They had a sand board. And the story goes that they said, come with us, old man. And he said, silence, do not disturb my circles. His last words. They killed him. Soldier really doesn't want to be told by an old man to not bother him. So that's how Archimedes died. Archimedes is in about 250 BC. So Euclid was 300 BC. Archimedes is 250 BC. Archimedes is going to be the one who comes up with pi. He's the one who comes up with the 22/7 approximation. Archimedes is the one that figures out that the area of a circle is pi r squared. Archimedes is the one who figures out the surface area of a sphere is 4 pi r squared. Archimedes is the one who figures out the volume of a sphere is 4/3 pi r cubed. And he does a lot of great math. He wrote about 13 treatises, and when the Library of Alexandria was burned down, most of the Greek work was burned and lost. But fortunately, Archimedes was considered so important that other cultures, particularly Arab cultures, had made copies of it. And so when the Library of Alexandria burned down, the Arabs had copies of it. So we have it today for that reason. So that's just a little like gist about Archimedes. Now I'm going to tell you about Archimedes in the context of the three problems of antiquity. So I've shown you that it's possible to bisect an angle with the two tools of compass and straight edge. So you can bisect an angle. But and you can cut an angle into 4 equal pieces, 8 equal pieces, things like that. But it turns out that they tried real hard, but one of the problems of antiquity is it possible to trisect an angle? And it ended up that that's not even possible with just a compass and a straight edge. They didn't know that until the 1800s. So in 300 BC, that was like a big question. Is there some clever way to trisect an angle? A second thing that you can do that I'm going to teach you about is what they call squaring. If you have like a polygon, like any polygon, but here I have a pentagon, to somehow use a compass and a straight edge to produce a square that has exactly the same area as the polygon. And I'm going to teach you how to square polygons today. But a circle is not a polygon. And as much as hard as they tried, they were not able to square in the circle. Squaring the circle was the second or number 2 of what in the order I'm telling you them of the problems of antiquity. How to use a compass and a straight edge to square a circle. It ended up being impossible, but they didn't know that until the 1800s. And the third problem of antiquity, if you have a square and you want to produce a square area, and you want to produce a square with double the area of the original square, notice how that's not double the width. Double the width would be 4 times. So it's actually, I'll say side square root of 2, and you get double the square. That we can do. But the third problem of antiquity is called doubling the cube. It would actually be a pretty good question on the final exam. Name the 3 problems of antiquity. I know I keep saying that it's basically a math test, but somehow I feel like throwing in a question of that importance wouldn't be any sort of violation of saying, and I think most people would appreciate a question like that. But no, not all the obscure facts that I said, but that would be a good question, I feel like. Those are the 3 problems of antiquity. If you type into Google problems of antiquity, you will see that's it. Those are the big 3. And these 3 problems kept mathematicians busy for thousands of years. Trying to do it, or proving that it's impossible to do, or proving that it's possible if I somehow like cheat a little bit, bend the rules a little bit, allow myself to use something aside from a straight edge and a compass, but not try to do the smallest amount of cheating as possible, maybe some other curve besides a circle. So we're going to look at all those today, the 3 problems of antiquity.
So Professor, just to be clear,
I'm going to start.
Yeah, just to be clear. So the 3 problems of antiquity are the things that can't be done?
That's right. Okay. The three things that really bothered them, that they were unable to do, and they didn't know this, but they were actually impossible to do. Okay, now here, we're gonna start with squaring, squaring. Now you could square other things. So squaring polygons, which will lead us. I want to show you that you can square a polygon, but there's some math I want to review first. And the first one is this. Here are some similar triangles. You actually can see this. It's the first question here. So with these similar triangles, notice how there's an X in both places. So they're the same size. The base of this, the short leg of the big triangle is equal to the big leg of the small triangle. Anyway, take a minute to calculate that. And I will. There you go. Some grants. I like that. Let me bring up my dashboard and see.
Professor, do you want us to put that in Desmos?
Yeah.
Yeah.
Yeah, put your answer into the Desmos. I'm bringing up the Desmos dashboard now. And this Desmos thing is pretty amazing that I could bring up this dashboard and see everybody's work. I only have 10 answers though, but okay. Oh. Okay, so yes, the answer is 6. And the work for that would be 9 over x equals x over 4. Corresponding sides of similar triangles are in proportion. I like to think of it as like big leg over small leg equals big leg over small leg. Some people might think of it as big leg over big leg equals small leg over small leg. You still get 9 over x equals x over 4. 36 equals x squared, x equals 6. So 6, and this thing actually has a name because when something satisfies an equation like this, we say x is the geometric mean between 9 and 4. Notice how that's compared to the arithmetic mean, which is 9 plus 4 over 2, which is 6.5. So they're different things. Arithmetic mean, you add them and divide by 2. Geometric mean, you multiply them and take the square root. The Greeks defined, I think, about 12 different kinds of means. The arithmetic mean, the geometric mean, the harmonic mean, the subharmonic mean. These are the only 2 that are relevant to us, but it's kind of funny that they thought of all these. And they weren't like statistics things, they were like mathematical things, the various means. Now, take a look at this picture. And this is also, like I said, there's a lot of slides, there's 17 of them. So here is a question with a right triangle, and then there's an altitude drawn to the hypotenuse of that right triangle. And we have a 9, AD is 9, and DB is 4, and they want to know what's the length of the altitude to the hypotenuse of the right triangle. Go ahead, take a minute to think about that. You can put that onto slide number 2. And yes, Tina, that's a good point. You could type your answer into the Desmos, but don't type the answer into the chat sort of publicly, just to give people a chance to think about it. Okay, I'll give you a couple of minutes to think about this. Okay, let's take a look. Now I see some people trying to use Pythagorean theorem, which there are a lot of right triangles in this picture. But the insight that really helps in this picture is to notice that there are 3 right triangles in this picture. A big green one, a small red one, and a medium-sized blue one. And they're all right triangles because, of course, they all have a right angle in them. But what's not so obvious is that they're all similar right triangles to each other, because the blue one and the green one both have this angle in them. The blue one and the green, the big one, so let me just move out can I get rid of the red? So the blue and the green, okay, this is becoming a mess. The blue and the green share, the blue and the green are both right triangles that have angle A in them. But the red and the green are both right triangles. The red and the green, sorry, green's the big one. The red and the green are both right triangles with angle B in them. You just need two angles. If 2 angles are equal, the third one must be, because they all have to add up to 180. So 2 angles is all you need for similarity. So both the blue triangle, the medium one, and the red small one are similar to the big one, which means that the red and blue are similar to one another. So I can say long leg of the blue over short leg of the blue is equal to long leg of the red over short leg of the red. And we end up with the same question as before. As a theorem, some people say the altitude drawn to the hypotenuse, the length of the altitude drawn to the hypotenuse is the geometric mean of the portions of hypotenuse. It's hard to describe it. All you need to know is if you see a picture like this, which you will see, this is the relationship. And this itself makes for an excellent question on the final, knowing this relationship about right triangles. Now, here is a rectangle. And I'm going to show you what the process is to so-called square the rectangle. We don't know what the lengths of these sides of this rectangle is, and we don't need to. I'm going to show you a construction that produces a square that has exactly the same area. And it goes like this. Step 1, extend AD so that DE is the same length as BD. Step 2, find the midpoint of AE. Not the midpoint of AD, but the midpoint of AE. Step 3, make a semicircle. I'm going to call this point F. Step 3 is to make a semicircle with F as the center and AE is the diameter. Step 4, extend BD until it hits the semicircle. And finally, step 5, produce a square that has DG as its side. And I claim that that square has exactly the same area as the semicircle. Let me just see, let me just look at this for a second. Okay, so we're not ready for a question on that yet. Would you think for a minute, this is really a good one to talk about in groups for, even if it's just for 5 minutes. So in your groups, talk about why should that square have the same area as that rectangle? Okay, let's do let participants choose rooms.
Professor, before you go, when you say same amount of area, that's the rectangle and the square together, right?
No, the rectangle originally had some area.
Okay.
Imagine the rectangle's area was originally 12.
Yep.
That square will also have area 12.
Okay.
That they have equivalent areas.
Gotcha. Thank you.
So why don't I make 6 breakout rooms? I forget how I usually do it. 1 through 4 are teachers, 5 and 6 are majors. Talk about this for about like 5 minutes. Why do you think, how can you convince somebody that the square must have the same area as that rectangle? Okay, Joan? Are you there?
Yes, Professor, I'm here. I was finishing to the diagram. So now I'm gonna join one of the groups.
Okay, great. Hey, everybody, welcome back. I accidentally kicked myself out of the meeting and then I had to re-log in. So in the Google Classroom, there's a link that says, it says Greek geometry for Mr. Rubenstein's math explorations class. When you go there, you get a link, you get basically a sketch of everything and more that we learned. Just look at how many things there are. Some stuff we haven't done, but everything we have done is in there. Golden ratio construction. One of them is Euclid Book 2, Proposition 14, squaring the rectangle. I should have put this up before. Check it out. It's kind of look at. Here's the first step. Here's the second step. Here's the third step. And here's the square. At least for this one, you can see the square has the same area as the rectangle. But what's nice about this is that you can change the dimensions of the rectangle and see how the construction would look for that different rectangle. So it definitely seems to work for these examples, but why should it? Anyone want to volunteer, like to describe, or if you came up with that in the groups, why is this square the same area as the rectangle? What about these steps makes it so it must be true?
I think step 3, the semicircle, like it's a big element that connects the two. And I just kind of figured out as you're moving that diagram, no matter what you
Yes.
did with the dimension, the semicircle kind of showed I'm gonna keep these things together. So I feel like the key step was the semicircle. Besides that, I'm not really sure, but yeah.
Hey, Professor,
You are right. The semicircle is the key. What's so special about the semicircle?
I feel like
Anyone else?
yeah, can you hear me?
Yeah. Yes.
So I feel like the area of the semicircle that's outside of the rectangle and the square is equal to region 3. And that little edge off of C, I feel like if you cut and pasted it, it would fill in the semicircle. Is that
I
true?
see. Very interesting. There's sort of like there's if you cut out those arcs, those pieces of circles, those aren't going to work into the explanation at all. But there is some stuff going on there. That's interesting. If the square and the rectangle really do have the same area, then it kind of reminds me of like the proof of the Pythagorean theorem that we once did, where they were like pieces that you rearranged. I'm glad you're thinking in that way. But actually, this is not going to involve those at all.
All right.
Any other thoughts about what's so special about the semicircle?
Could we form? I was thinking forming triangles because you have this sort of midpoint F, which is the center of the semicircle, and connecting F to G and G to E. The fact that you have these two triangles.
So
F
some
to G.
triangles with F and G. There is a way to do something with that, with those triangles. Do you remember on the very first day of Greek geometry, we did our first 4 theorems were triangles add up to 180 degrees,
Thales
exterior
theorem.
angles equal Thales theorem.
Yeah.
Well, Thales theorem is what is the key to this question, because if you were to draw in these 2
Yeah.
lines,
And we see, yes.
what could you say now that you couldn't say before?
This is the right triangle.
Right triangle, yes. So what we end up with is the right triangle configuration that we did over here. But it was hidden because those 2 lines weren't in the original picture. But now I can call this, I'm just going to call this X right now. And we can say that that's the mean proportional AD over X is equal to X over DE, which is the same thing. DE is the same thing as a DG, or X squared equals AD times DG. In other words, that's the area of the rectangle. And then this is going to be the area of the square. So this is a very slick usage of Thales theorem and the
Professor,
mean proportional. Yes?
you write X only the length of the rectangle, dV.
So AD and DE are the 2 things we're using, because those kind of equate to these 2 lengths. But this isn't actually the length of it. We made it to be the same length as the side of the other side of the rectangle. So
So you
maybe
put X dE or X dG. This is the confusion.
yeah, maybe we like it better like this. If I call this Y and Z,
Mm-hmm.
and call this thing X, Z is also over here. Because this length, which I'm going to highlight now, this length here was produced to
Yeah.
be the same length as this. So using just all letters, we would say that YZ is equal to X squared. But YZ is the area of the rectangle. And X squared is the area of the square. So that's really slick. If you don't have this right angle in the top there with Thales theorem, you can't do this proof. It's necessary. So that semicircle was very important. Now you wonder, okay, how does this come up on the final? Look at this, question number 3. If AD equals 10 and AC equals 3, what is the area of the square? So you can go ahead and put that in to slide number 3.
Can you put the values up again? They just disappeared.
Yes. 10
Oh, okay.
10 and 3.
Let's
I
see.
could actually this thing's nice because I made it a sketch that you could actually write on. Okay, let me take a look at slide 3. Good. And yes, the answer is 30. Because that's what this construction is. I would want you on the final to recognize, oh, that's the squaring of the rectangle construction. So if the rectangle's area is 30, then so is the square's area. This 3 here is just from D. I didn't even name this point here, but the area is 30. If they asked, the side of the square would be square root of 30, but it's not what they asked. I heard one group was discussing, like, they worried about the final, and this is when you look at a question like this, which I put on the final from time to time. I mean, the final I think is 30 questions, but it comes from a bank of 100 questions. You know, I just not gonna make a 100 question final, but you'll probably study 100 different things, hoping that the 30 that come up on the final are the 30 that you're comfortable with. But this question, I'm hoping these things are like mind-blowing. So it's like, you're like, wow, that's a great construction. So surprising. So that when this real recall question on the final comes up, just find the area, what's the area of the square? Someone who really has been following along is going to know that answer, you know, instantly. But someone who's not really following along, who's kind of has the class up kind of in the background while they're doing all kinds of other things. Of course, in live schooling, people could daydream and not you know, be engaged also, but it's easier to do that when you're on Zoom. So usually people do pretty well on the final. Usually most people get like 80 or higher on the final, but for whatever reason, every time there's been 1 or 2 people who just get significantly lower. Like, it's like people are all clustered, you know, 75, 80, 85, 90, 100. And then there's like 2 people who get like a 30 or something. I hate to see that. It's a college class, and I'm not able to, or should I really make sure, you know, the way I do in high school, you got to make sure every single person is following along. It's just not what you do, and I try to do my best, you know. But don't be. Let's make this the year that there's not two people that get like a 30 or 20 on the final. So I'll keep going. But the final, if you think looking at it now, if you say that's a pretty fair question, if this came up on the final, I feel like that was not like a nasty question in any way. It's about as easy of a question about this topic as opposed to saying, name all the steps it takes to square the rectangle. That would be like a harder question. That's not what this is.
Okay, so question, something like this, would we have to show our work, like the way you put in the,
No.
or just giving the answer?
Right. On this one, it would just be giving the answer. There could be questions that have you show a little bit of work for something, you know, particularly, you know, Egyptian false position. You know, there are ones where I want to see all the steps that those are worth more points. But this would be like a 5-point question. No work to be shown on it.
Got it, thanks.
Okay, so we have done squaring the rectangle. Well, what if it's not a rectangle? What if it's a triangle? Well, they do something sneaky. They take the midpoint of the triangle side and they create a rectangle. Here's the parallel side there. They create a rectangle that is literally area equals half the base, half the original base times the height. So the rectangle is 1/2 base times height, and of course the triangle is 1/2 base times height. And then they square that rectangle. This is not drawn to scale very well. Why don't I just say, to square a triangle, turn it into a rectangle by taking the midpoint of the base of the triangle and creating a rectangle that will have the same area as the triangle. They're both 1/2. Yeah, why don't I call this up? I'll say X is the entire base and Y is the height of the triangle. So the triangle is 1/2 X times Y, but the rectangle is 1/2 X times Y. One's 1/2 base times height, the other one's base times height, but the base of the rectangle is half the base of the original.
Wait,
So this is,
I can't.
yeah.
Where's the rectangle? Where's the rectangle in relation to the square in relation to the I'm having a hard time seeing it because it's all in blue.
Yes, I didn't make the square though. So
Okay.
here's a triangle.
Okay.
And here is a rectangle that has the same area as that triangle. Because it's made off the midpoint of the triangle and it has the same height. Now, I would then forget the triangle altogether. And then I would square the rectangle, which already looks a little bit square-like, but not exactly. So the square has the same area as the rectangle, but the rectangle had the same area as that triangle. So it's kind of like, they call that reducing one problem to another. I know how to square a rectangle. I don't know how to square a triangle, but if I can turn the triangle into a rectangle, I can square that rectangle. And in doing so, I square the original triangle.
So the square equals the rectangle equals the triangle.
That's right. And the squaring the triangle did not require very sophisticated reasoning. Sorry, rectangleizing, if that's a word. Rectangling the triangle looked like that. It was just based on the fact that a rectangle's area is 1/2 base times height, and a triangle's area, a rectangle's area is base times height, and a triangle's area is 1/2 base times height. So if my rectangle has the same height as the triangle, but the base is half the base of the original triangle. So turning the triangle into a rectangle is real straightforward. It doesn't have a semicircle involved or anything like that. Now, squaring a polygon, let's just say I have some random quadrilateral. We would cut the quadrilateral into two triangles, and you could do this with any polygon if it's got, you know, a lot of different sides. You can always cut it into triangles. So you would turn the polygon into triangles. Each of those triangles would get squared. In this one, there'd be a whole bunch of squares. And then real sneaky, this is two different squares. I want one big square. So you would use Pythagorean theorem, put these squares onto the legs of a triangle, and then the hypotenuse would become the sum of the two squares. And if I have more than two squares, I would have to make, you know, a little tiny one to combine these two, and then take this one and put this together with it. It's not that important. I just wanted to show you that you could square any polygon eventually. But a circle is not a polygon. And squaring the circle is really hard and actually impossible with compass and a straight edge. They actually still use the expression squaring the circle in like the English language to mean like trying to do something that's impossible. And somebody who claims that they did something that was impossible is sometimes called a circle squarer.
I'm sorry, Professor, one question. So you use the Pythagorean theorem in the previous polygon for each of the triangles to create these squares. Am I right?
No, once I had, so the steps would be first I would go through a process of, I'm just giving the outline of it. I would square the two triangles.
The way that we did earlier with the rectangle.
The way we did earlier.
Right.
That's right. And then I want to combine them into one big square. So I do that by assembling the two squares I just got into a right triangle. And then since a squared plus b squared equals c squared, I would get a hypotenuse. And if I produce another square, that would be the sum, and I could keep doing that. We're never gonna have to do that. I just wanted to let you know that any polygon can be squared it could have 100 sides. It could look like a circle, but it's not a circle, it's a polygon.
Hey, Professor,
Squaring the circle, yes?
did they find the Chinese, because that kind of looks like what the Chinese were doing with Pythagorean theorem, right? No? With the squares on the outsides?
Oh, well, the Greeks had, the Greeks also had Pythagorean theorem that they interpreted geometrically. So remember yesterday we did the Euclid's proof looked like that, except it was, it was upside down.
But do you think they ever, with the Chinese? So, I mean, because there seems to be a little kind of, now that I see this, like all these squares on top of the sides of the thing, was there any connection between Greek math and ancient Chinese math?
Well, they're around the same time period, so it's hard to know, if someone traveled. I know the ancient Greeks went to Egypt, like Pythagoras and Thales. They went to Egypt and learned. So a lot of times we pretend that that Greek somehow made this gigantic leap from Egyptian to Greek, but they actually learned it from the Egyptians and just or we don't really know what the Egyptians were doing around the time of the Greeks. We give the Greeks, a lot of credit, and maybe they don't always deserve all of it, but they did a lot. Circle squarer in like the 1940s, more so than now. We don't run around saying that someone's a circle squarer if they are attempting to do the impossible or claiming they do the impossible. Circle squarer definition. It basically means a quack, somebody who's thinks they do something, claiming they can do something that's impossible. Square the circle, idiom, to solve or attempt to solve an impossibility. Square the circle, say to try to do the impossible. 1624, go not thou about to square either circle, God or thyself. Common idiom, square the circle, do something that's considered impossible in the literal sense. Square the circle. The government is trying to square the circle when it says it will spend more on the health service without raising taxes. Anyway, just wanted to let you know, square the circle. It's not really a common expression nowadays, but there was a time where if you said that, people knew that you meant, and fairly recently, like the 1930s or something like that. Okay, I'm going to put aside where we are now is that it's possible to square a polygon, but I'm going to put aside the squaring the circle till later. Oh, actually, I rearranged it, so I am going to do it now. Anyway, there's 3 goals for today. Show you how different attempts, different accomplishments in squaring the circle. Then we do trisecting the angle, and finish out with doubling the cube. Now, squaring the circle is where you have a circle, and somehow you create another circle that has the same area. If the radius of the circle was 1, the area would be pi times 1 squared, which would be pi. So this square would have to have the square root of pi as its side. There is also something called rectifying the circle. Rectifying the circle is where you create a line segment whose length is equal to the circumference of the circle. If the diameter was 1 in this one, the circumference would be pi times diameter. So if I could make a line segment whose length is the same as the circumference of the circle, that's called rectifying the circle. And Archimedes showed that if you could solve one of these questions, you could solve the other one, because he showed that the area of a circle is equal to so back then they know circumference is pi times d, and he would say the area of the circle is 1/2 the circumference times the radius. In other words, if he made a triangle, I'm going to call this R. If he made a triangle that had 2 pi r as the base, circumference is the base of the triangle, and the height of the triangle is the radius of the circle, that circle, the area, would be 1/2 base 2 pi r times height, which the 2's cancel out, and we get pi r squared. So Archimedes showed that the area of the circle and the circumference of the circle were related by whatever this pi was going to be. And it also showed that if you could rectify the circle, if you could get a line segment that's the same length as the perimeter, you could produce a triangle that has the same area as the circle, and that triangle could be squared to make a square that has the same area as the circle. So part of rectifying the circle is coming up with an exact value, if possible, of pi. Now they knew back then, and I'm just going to refresh your memory. If you take a circle and you take the diameter and you kind of lay it out over here, it wouldn't quite reach half the circle. Wouldn't be a semicircle. And if you take a second one, it would be past the semicircle. And if you take a third one, it wouldn't quite make it fully around the circle. So we know that pi is bigger than 3 because pi is how many diameters fit around the circle, or as they say, the ratio of circumference of diameter. There's more than 3 diameters around a circle. And then the question is, this little tiny piece, what is it?
Pi is greater than 2 or 3.
Oh, and it's less than 4 also. But what is it? Is it 3? Is it, 3.5, 3 1/4, 3 1/5? What is this little piece?
Yeah.
Well, it turns out that little, yes, it's about 1/7 of the diameter. Not 1/8. 1/8 is too small. 1/7 is good. 1/6. 1/7 is actually a little bit too big. So it's between 1/7 and 1/8. So some cultures would say 3 1/8. Basically, it was close to, that's pretty close. But Archimedes figured out that pi was less than 3 1/7. But that wasn't good enough. He also liked to get, what is it bigger than? Because anything could be less than 3 1/7. That's the 22/7 that we're so familiar with. He also showed that it was bigger than 3, and this is so close to 1/7. Look at the way he writes it. A little bit less than 1/7, I should say. So 1/7 is 10/70. And he shows that it's somewhere between 3 1/7 and 3 and 10/71. So he gets this bound, they say. And he left it at that. Both of those numbers, if you turn them into decimals, have 3.14 as their digits. So some people say, well, Archimedes is the one who came up that pi is 3.14. But no, our Archimedes said that pi was between 3 and 10/7, 3 and 1/7, which is 22/7. That's the upper bound for pi. But he also found a lower bound. And it's really nice, this result, to say 3 1/7 and 3 and 10/71. Now, you could get more accurate than that. He didn't want to. His process could have yielded even higher accuracy, but that wasn't his goal. His goal was to have this nice relatable estimate, 3 1/7, but greater than 3 and 10/71.
Did he realize pi was irrational then?
No. So he might have suspected it. The only irrational numbers they had were like the square roots and cube roots and things like that. So the idea, they didn't prove pi was irrational until like the 1800s. So I don't know that and I've never seen any discussion about when they showed that square root of 2 is irrational, they have a process for doing that, like a proof. But to do it with pi, it doesn't work. That proof, you can't. It wouldn't work if you used something like pi. So, but he probably suspected that it was irrational, since they knew about irrational numbers.
Not only
Now,
that,
how does he do it? Oh yeah.
yeah, if you
Go
keep
ahead.
going through his process, the difference isn't going to be that great. Like, it's a lot of work to get like a tiny bit of difference, which is why it's pretty well approximated by 22/7. To where if you look at something like the golden ratio, it's not quite like that at all. That's why it doesn't have a fraction that approximates it.
That's right. The golden ratio, there are fractional approximations, but they takes 3 1/7 is actually very, very good approximation, more so than golden ratio approximations. Now, Archimedes gets his value for pi by using two theorems, only two geometrical theorems. Maybe I guess I could say three. The theorems that he uses are the Pythagorean theorem. Actually, he just uses two. Pythagorean theorem and an obscure theorem that is called the angle bisector theorem. So I need to show you what that is. Using just those two things, he is able to get his bound for pi. So what is this mysterious angle bisector theorem? Here's a question for you to do on the on page 5. Oh, that's weird. That shouldn't be. Where is it? Oh, I don't have it. It's just do it on here.
Isn't it page
Here's a
6?
picture.
Page 6?
Oh, it is page 6?
Yeah.
Let me look at that. Maybe I needed to reorder my stuff. Strange. Sorry, I didn't. Page 6 is kind of in the wrong place, but go ahead to page 6. I have my pages are in the wrong order. Okay, so page 6. What do you think of this picture? Here I have an angle bisector. Does it say it? Yeah. So page 6, everyone.
Does that shading tell us that it's been bisected, or are we trying to prove it's bisected?
No, it's given that it's bisected.
Okay.
So maybe I should go like that. It's kind of that shading is saying. Oh, so you don't have access to the Desmos, but on the Desmos it says this already is an angle bisector, so it is. It's given to you, and they want to know. And people have written that the answer to this first one is 4. In the case where it's an isosceles triangle, in an isosceles triangle, the angle bisector is also the perpendicular bisector. And you could prove that all kinds of ways. Easiest way would be SAS. Right, these 5s are equal. These are equal, shared side, reflexive, and these angles are congruent because it's told to us that it's an angle bisector. So by SAS, they're congruent triangles. So if this is 4, that's also 4. But what if it's not an isosceles triangle? Now you might suspect that it's 4, except it isn't. In general, angle bisector. In general, the angle bisector is not also the so-called median. And this is a very hard question. If you want to fiddle around with it for a couple of minutes just to appreciate how hard it is, go ahead and fiddle. Actually, when I put you back into your groups, you could just like discuss the difficulty of this question very carefully. I'll put you in for like just a couple of minutes. Hey guys. Okay, did anyone, just wondering, if it's not 4, which it isn't, is it bigger or smaller than 4? At least we could talk about that. Did anyone get an answer for it? You could just unmute and say it if you have one.
I'm gonna spitball this. Is it involving and drawing an auxiliary line off of C that's the length of 6? So that you could create a proportion?
Well, it's definitely going to involve an auxiliary line.
Okay.
And I'll show you what that one is in a second. But before, did anyone just have a numerical answer that they like somehow came up with? I was curious. I'll show you what the auxiliary line is in a second. Okay, so this is so math majors wouldn't be aware of this theorem either. Like they teach it in geometry sometimes, but in college usually don't take like a Euclidean geometry course. Okay, here, check it out. There is an auxiliary line.
You can draw one.
The auxiliary line is.
You can draw one parallel line with the base.
Well, the line is going to be a line parallel to the angle bisector.
Yes.
Coming from B. And then extending AC until they reach. So it's going to look like this. Like that. So what's important about this? Very important that those are parallel to each other. So what might happen now that there's this extra 2 lines, right? I drew in this, 2 lines were drawn in, a red line, and I extended AC.
Did you create transversals?
Yes, there are transversals, which means that not only are these 2 angles equal, but this angle, because I have a transversal, so it's like the letter Z here, is equal to this angle. And this angle here is equal to this angle here by corresponding angles.
So is that a trapezoid then?
Well, it is a trapezoid because of the you got the parallel sides. But more importantly, it's not the quadrilateral that's so important. But what's important is the isosceles triangle. You see, this angle was equal to this guy, and this angle was equal to this one. But because it was given that this is an angle bisector, that made those 2 angles equal, which makes all 4 of these angles are equal to each other.
Yeah.
Which means that this 6 over here is also the length of that green side.
Yes.
And now, what 2 words are going to be key at this point to figuring out what X is?
Similar triangles.
Similar triangles. If I were to now get rid of this line here, it would look like this. And because these are parallel, these would be similar triangles. It looks almost like right triangles, but it's not. So go ahead and answer what's X with similar triangles now. Take a minute on that. And I think that this will, I think it's on the next, no, it's not. No. You could type your answer into the chat now.
All right, I'm gonna go for it.
Okay, someone have a numerical answer? Yes, 24/5. There's two ways to set this up. Most people, their instinct would go 5/4 as 11/4 plus x. Because the 5 and the 4 are the sides of the small triangle, and the 11 and the 4 plus x are the sides of the big triangle. 20 plus 5x equals 44. 5x equals 24. Now I'm going to tell you something that's going to come in handy. Another proportion that would have worked for this question, although this is going to seem kind of weird if you've never seen this before, believe it or not, even though the 6 is not a side of a similar triangle, it's a piece of a side of the big triangle. If you did 5/4 equals 6/x, it would get you the same answer.
Huh.
You are allowed to do that. That's actually a theorem in geometry also, that if you ever have this situation, you can go piece over piece equals piece over piece, and it will work. I'm not going to even prove it. I'm just going to say that's a little shortcut. And the reason I tell you that is because this will lead us now to the so-called angle bisector theorem. Here it comes on its own page. I'll just go like this. I'm going to say it first. Just going to give you the theorem. Angle bisector theorem. I'll just say by angle bisector theorem. Here it comes. You say the two pieces that make the angle, the ratio of those is equal to the ratio of the two portions of the side that got divided.
Oh my God.
That's called the angle bisector. Let me write it up this way. A, B, angle bisector, CD. You can say A over B equals C over D. I give that to you. There is a hidden similar triangle, but that's okay. You now know the angle bisector theorem. A over B equals C over D. And that's a theorem we're going to add to our toolkit. It's a funny theorem because looking at the original picture, we don't see any similar triangles at all that might come in handy. But it's when you draw those auxiliary lines that we see A, C, D, B, B. A over B equals C over D. Angle bisector theorem. Good news for you. With that theorem, you can very easily do, it will only take a second. Oh no, you can't do it, sorry. Still a little bit hard. So, angle bisector theorem. Let's redo. So there's different configurations.
Could you shrink that so the whole thing is showing? Because I only see part of it.
Oh.
It was just the words in the very top of the diagram.
Oh, because that was the Desmos. The Desmos, I have to like scroll to see it all.
Okay.
So an example of a question that we can do, if the given information, I like it when it's like this, 10, 6, angle bisector, and they tell us one of the pieces and ask us to find the other piece. That's the easiest case. So go ahead, just for fun, what is X in this case?
Want us to put it in the chat?
Yeah, just throw it in the chat. Yes, the proportion is going to be 6/10. equals 2 over x. So we like the angle bisector theorem, but there is another way I could, there's another way to apply. This is ideal if these are the 3 pieces of given information and you're asked for the other piece. But let's look now at this question. And this is actually also question number 4. I'll put it up like this. It says CE bisects BCA. But look what they tell us now. BC is 6. AC is 7. And unlike before, where they told us one of these pieces and didn't tell us the other, they're telling us AB is 5. And they want to know how big are the 2 pieces that add up to 5. Take a second to think about that. How can you get, it's not 2.5, 2.5. What is it? Go ahead, ponder that.
We can
Give
write
you a minute
I
to
equal by 5 minus x.
Yes, that's right. So work that out that way.
So do you make one x and the other 5 minus x?
Yeah.
Yeah, that's right. That's exactly right. It doesn't matter which one, but yes. So once I have the 5 minus x and the x, I could erase the 5 now. And my proportion, 7 over 6 equals 5 minus x over x. Cross multiply, 7x equals 30 minus 6x. 13x equals 30. X equals 30 over 13. And 5 minus x is 65 over 13 minus 30 over 13 equals 30.
Oh, sorry.
So that is the angle bisector theorem. And it's going to be very common that the 3 sides of the triangle are known, and we're trying to find these 2 guys. Now, sometimes after you do one of these questions, so now I have 35 over 13 and 30 over 13, they want to do it again. They want to take the angle bisector of one of the pieces. And now they want to know, what are these 2 things? We can't do it though. Why not? We're in trouble.
We don't know what EC is.
That's right. But we don't
But
know
we will.
EC. So we can't go. We can't do it again. Unless, here it is, one of my favorite questions. If the triangle happens to be a right triangle,
Then you can find the hypotenuse.
Yeah.
then after you get EB, so they want EB, but then you can get, you get EB and AE from the angle bisector. But then you can get EC by Pythagorean theorem. And just to make this extra fun, I'll put you in groups for a few minutes. I'm going to throw in one more line now and say that our goal is to get BF is the goal. EC by, and then you can get BF with angle bisector. So here I have a question for you. I have 3 and 4. 3 is CB. AB is 4. And very important, I have a right triangle. And I want you to find 4 things. BE and AE, then EC, and then BF. I'm going to put you into groups for about, and then we'll take a break after this question. I'll put you into groups for for 8 minutes. We'll come back, go over this, and then take our break. So I'm putting into groups to talk about this. I do believe that this is a, I think it's question number 5, except question 5 just says BE and AE. It doesn't say also get EC and BF, but I'd like you to try to. So 8 minutes in the breakout room, see if you can get all 4 of these answers, and here
Wait.
you go.
Could you show
Okay, so I hope you came up with the first step, which was to get 1.5 and 2.5 as the lengths of BE and AB. We call those X and 4 minus X. It actually doesn't matter which one you call X and which one you call 4 minus X. And of course, we needed to use Pythagorean theorem in the beginning because they didn't tell us the hypotenuse, but fortunately we had this right angle, so we were able to get it. Now, if I take this little triangle, ECB, and I copy it like that, now the sides of that triangle, see, BC is still 3, but we just figured out that EB was 1.5, and we're going to need the hypotenuse to do the angle bisector theorem. So we have to actually do a little Pythagorean theorem there. I just approximated to 3.35. And then I do the angle bisector theorem again, this time calling the sides y and 1.5 minus y. And I ended up with about 0.68. I think it's right. For some reason I didn't have the answer. Anyone else get that same answer with their groups?
No, I didn't. No.
Yeah, we got there.
Okay, I guess I'm confused on the math then.
I might have got, I didn't have the answer handy. Well, the first question is, did you have 3.35 as EC?
Yeah.
Okay, so then our proportion is going to be 3.35 over 3 is equal to 1.5 minus y over y. Cross multiply 3.35y. 3 times 1.5 is 4.5 minus 3y. Add, oh yeah, I see, I made a mistake. It's 6.35. So
Yeah.
it's 4.5 divided by 6.35. Thanks. So let me fix that.
Yeah.
4.5 divided by 6.
Approximately
And we get
1.41.
0.71. Sorry about that. Now, one of my
I
favorite
reversed the order.
questions, if you glance, we're not going to do this question now, we're going to take a break, but for homework, there's something like this. It looks like, hold on. This is the one we just did. Is there another one? No. Anyway, I'd like to give this question on the final. I give you a right triangle. I tell you 2 of the sides. And I draw in 1 angle bisector, 2 angle bisectors. And I ask, how big is that? That's one of my favorite questions to ask. So really likely to come up on the final. Okay, let's take 10-minute break now. We'll come back and do more and see how does Archimedes, now that we know what the angle bisector theorem is, how does Archimedes use it to calculate pi? That's coming.
Before you log off, can you put the screen
I'm
back?
here. I'm here. My camera was just off. Yeah.
Yeah, can you just go back to the prior screen so I can see that solution, please?
Yes.
Thank you.
Okay, everybody. Welcome back. In the Google Classroom, there's a couple of other links. For instance, this is what I wanted to show you. Angle bisector in a right triangle. And if you click on that, it actually lets you, this is kind of neat, it lets you adjust the dimensions of the triangle, so you can kind of see what the answers are going to be and make sure, because there's a homework question like this. Let's let this load up first. Okay, so what this does is it lets me, like for instance, that one I just did, which had 3 and 4. I can go like this, 3, 4. And it actually makes it makes 1, 2, it makes 3 angle bisectors, which would take even more calculation because you'd have to calculate out 2 hypotenuses. And it tells you the length of everything, CF, CG, and CH. So notice we got 1.5 and 0.71. This is showing that if you went one step further, which would be hard because you'd have to get GD using Pythagorean theorem again, that would be slightly bigger than 3, and then do the angle bisector again. But what's nice about this is I could change the numbers. I can make it, whatever I want. And you could practice this because, as I mentioned, this is a question I really like on the final. I usually don't make 3 angle bisectors. I usually just make 2 angle bisectors. So just give you FYI about that. Now, what does this have to do with pi? Well, if I come over here, there's one that says Archimedes upper bound pi. And let me give you the general idea first. But as this is loading, I'll say general idea is that he's going to get the perimeter of a regular polygon. And his first approximation is going to have just a hexagon circumscribed around the circle. And he's going to calculate the perimeter of that hexagon to be about 3.5. And then he's going to be very slick. He's going to make an angle bisector. And that's going to, whoops. Sorry. Then he's going, I'll go this way. Then he's going to bump up his approximation to 12 sides. And I'll show you how he does this. But the 12-sided figure is closer to being a circle. And the perimeter of that ends up being about 3.2, a little bit bigger than pi, but closer to pi than before. Every time he does it, he's going to double the number of sides. So on the third step, he's going to get the 24. You just call it 24gon. Its perimeter is 3.16. He's going to go on to the 48gon to get a perimeter of 3.146. And he stops at the 5th step. He finds the perimeter of a 96gon. It's practically a circle, but not. And the perimeter of it is about 3.142. Now, he could have kept going, but he didn't. And he could have stopped earlier, but he didn't. The reason he stopped at step 5, not before step 5, and the reason he didn't keep going beyond step 5 is that this is the first time that that perimeter is less than 3 1/7. So all these other ones were slightly bigger than 3 1/7. And the next one is also less than 3 1/7, but he didn't need, he went just as far as he needed to get the really pretty result that pi is less than 3 1/7. So it's not just accurate, but it's like a really nice, relatable number. Now, how does he do this? The general idea, actually, I need to come over to the iPad for this, so hold on. Okay. Let's start with the circumscribed hexagon. Now this circle, I'm going to choose to make the radius 1/2. That way the circumference of the circle would be 2 times pi times r, which would just be pi. So the circumference, not only is pi the ratio of the circumference of the diameter, but in this case, pi is the actual circumference of the circle itself. Now, a hexagon can be split into 6 isosceles triangles. And while I'm at it, a 12gon can be split into 12 isosceles triangles. I have this extra line here. I'll tell you about that line in a minute. So hexagon could be split into 6 isosceles triangles. And each of those triangles can be split, since they're isosceles, can be split into 2 right triangles. So the hexagon can be split into 12 right triangles. So here's his plan. His plan is to examine one of those right triangles and see if he can figure out the length of the leg of that right triangle. Whoops. I don't need all this. Now that right triangle was half of this triangle, and this triangle is actually, this angle here is 60 degrees because 360 divided by 6 is 60. Whereas over here, in the 12gon, this pi slice, its angle would just be 30 degrees because there's 12 of them that fill up the circle, basically. Notice 30 is half of 60. That's relevant. When I split it into 2 right triangles, this would be a 30-degree angle, and this would be a 15-degree angle. So those are also irrelevant that it's half as big. Now, this triangle, it's an equilateral triangle. Now, in an equilateral triangle, let's imagine it was an equilateral triangle with 10, 10, 10 as the sides. And I want to know what's the length of the altitude. Now, some people have it memorized, but how can we use what we've already learned to get that answer? What do you notice? What's sort of the simplest way? Some people might have it memorized, 30, 60, 90, stuff like that. But if you don't have some stuff memorized, how could you use just stuff that has come up in this course already to find the length of the altitude?
So we use the bisector angle theorem to find.
Oh, you could use the bisector angle theorem, I suppose, and find, but you don't need to in this case. Just because this is a 10 and 10. The angle bisector theorem would tell you how big these two things are.
Right.
But we don't need it for this one. Why is that?
I guess we could use Pythagorean theorem. And because the bisector is the midpoint, right? We had a rule as well. So
That's right.
wouldn't that be 5 and 5?
That's right. So we can use Pythagorean theorem after we
Yeah.
realize that this triangle is, each of these is half the hypotenuse. Now, this is actually known as a 30, 60, 90 triangle. Some people might have not seen that in a while. In a 30, 60, 90 triangle, the ratio of the sides is that the short side is always half the hypotenuse.
Yes, that's true.
Now, the medium side, you do Pythagorean theorem. Square root of 10 squared plus 5 squared is square root of 125 is
5 square root of 3.
5 root 3. I'm going to write it as
No,
square root.
it's, Professor, it's 10 square minus 5 square.
It's not 5. Oh, minus? Oh,
Yes. And this is 5
Thank
square
you.
root of 3 is okay, yes.
Thank you very much. Square root of 75. I knew something was wrong with that. And you end up with square root of 75, which is 5 root 3. So a lot of people memorize that the ratio of the three sides in a 30, 60, 90 triangle are x, 2x, and x root 3. But it's really just a consequence of the Pythagorean theorem. So come back over here now. Here, whoops, let me just go like this again. Here's a 30, 60, 90. And usually it's nice when I know the small side or I know the big side. Let's cut it in half for the 30-degree angle and then slap a square root of 3 onto it to get the medium side. But very often it's the medium side that's known. Now, if the medium side already has a square root of 3 on it, it's real easy. You just get rid of it.
Yeah.
But what if the medium side does not have a square root of 3 attached to it already? What can you say about the other two sides? Or how can you express them?
We can say 2x hypotenuse and x the other side.
Oh, okay. We actually could do that. That's right. That is one way of doing it. We'll get a shortcut for it, but yes, I like that. X equals square root of 64 over 3, which is 8 over radical 3. And that actually is a shortcut we can do. You know, if you go from short to medium by multiplying by the square root of 3, you can go from medium to short by dividing by the square root of 3. You know what I feel like I'm doing? I don't know why in my whole career, I don't think I've ever written it this way, but I'm going to say x over root 3, 2x over root 3. I basically just divided everything by root 3, and I get like a new sort of relationship. So this would be 16 over root 3, because it's double. So now we come back to Archimedes. We have that the radius of the circle is 0.5. Yeah, I'll just call it 0.5. And then we can call this 0.5 over square root of 3. And this is going to be 1 over square root of 3. But if we take the 0.5 over root 3 and we multiply it by 12, I get 6 over root 3, which is about 3.5. So the perimeter of the hexagon is this length here multiplied by 12. And we can see in this page, we'd actually see that 3.46. BD is actually about 0.29. So this shows that pi is less than 3.5. But now comes the magic. If we then switch over, okay. Let me say it this way. Here's a picture of the 12-sided figure. And it's hard to see. Everything's so small on it. Figure that out. Now, see this side here? I'm calling that BD. If I could do 24 times BD, I would get an even better approximation for pi. 24 because there are 12 of these isosceles triangles, but each one's composed.
It's 24
this
times
little
what? 24 times BD.
Times whatever BD is.
Okay.
Let me write that nicer. Now, what's BD? Well, this entire angle, this one, is 30 degrees because it's one slice out of 12, which means this piece right here is 15 degrees. Now, remember the hexagon, which I'm going to actually put in the same. Oh, I'm gotta be careful here. Hold on. Okay, this is 0.5, just like before, and I want to know what this is. Check it out. Big moment right now. Let me make a copy of this. Here is the equilateral triangle that I used to make the hexagon. And here on the same picture is the isosceles triangle that makes up one of the 12 triangles for the 12gon. And all I really care about are these right triangles. And I know that this is about 0.29 and this is about 0.58. That was 0.5 over square root of 3 and 1 over square root of 3. And I want to get this. But check it out. Here it comes. If this angle here was originally 30 degrees and this angle here is 15 degrees, this blue line, or let me make a different color. This red line is, all together now, an angle bisector. In other words, this picture that we did before, where we know this is a right triangle, and we know 2 out of the 3 sides, and we know it's an angle bisector, we can call this x and call this 0.29 minus x. And when I figure out what this x is, that would be this piece right here, which I would then multiply by 24. Let's take a look, kind of like a cooking show. They show you the finished products. And they end up with an answer of 0.134. That's the length of this tiny little segment from here to there.
Where's the
But what
calculation?
did it do? Yeah.
Yeah, where's the calculation? You're trying to keep up with you.
Oh, it's over. So it's right over here. That's the angle bisector theorem. The way I taught it to you, you would write it like this: 0.5774 over 0.5 equals 0.2887 minus x over x.
So is that because you rounded 0.58 before, now it's turned into 0.5774?
Well, in this one I rounded to more places because I wanted to get a more precise answer.
I understand.
So I did 0.58 before.
I'm trying to connect.
I did 0.58 because if I was going to stop at that point, and just get the area, the perimeter of the hexagon, 0.58 would be good enough. But if I'm going to go another step further, because these numbers are so small that if I start rounding them, I'm going to lose a lot of my accuracy. Now, if this was I actually toyed with the idea of making the circle gigantic, making the diameter 1,000,000, instead of 1, so that we wouldn't have to. So our rounding, we wouldn't be thinking of rounding our decimals. We would just round to the nearest whole number then. But I'll do that next year. So round to 4 decimal places.
All right.
And as you can see over here, that's the next answer. And what I did in this picture, if I click here, show triangle, you can see the, here you go. Ha, of course, I made it like this. You can see the hexagon and the 12gon in the same picture now.
Yeah.
So it helps you see a little bit where this angle bisector picture fits in. And then, of course, if you do it again, you'll get the next answer, and the next answer, and the next answer. So you end up, Archimedes does it. He does this 3 more times. After he gets the 12gon, he goes again to get the 24gon, again to get the 48gon, and again to get the 96gon. You're going to redo those calculations as part of the homework. You can use this site though to check your answers as you go along, because you don't want to, if you have a wrong answer, you don't want to use it in the next iteration. Okay, and that's all I want to say right now about the pi. I did post a lot of videos. Like I have three pi calculation videos, and I have some stuff for you to look at. Here is a very cool picture. That shows the gist of what he's doing. This is 0.5 originally. This is 0.5 over radical 3 originally. And this is 1 over radical 3 originally.
Just a quick
And
question.
then,
I'm sorry.
yes.
Just a quick question. In the last iteration where you found that x was 0.134, that was the 12gon? Or that was the
It was
24.
half. It was half the size because so that was the length of this line segment, which is actually half the length of this segment. So I multiplied this by 24, even though I was trying to get the 12 gun, because that was only 1/2 of one of the 12 sides. So the thing I calculated with the angle bisector was half of a side of a 12 gun. So that's why I had to multiply by 24.
So you're finding the perimeter of 12 gone by multiplying by 24. So
Yes, and that's
when you
that's
do the
because if I
48,
come over here, yeah, you have to multiply it to 24 gun, because really it's this side. If you wanted to, you could multiply 0.134 by 2 to get this side to be 0.268, and then multiply 0.268 by 12. You know,
Yeah.
if you want to think, okay, 12 gone, I need to multiply something by 12, you could, but you'd have to first double the 0.134, because the 0.134 was only this tiny thing.
and you
It's
got
not
the
even.
and you got the 0.5774 from the previous iteration.
Yeah, I mean, I'm having the same problem. It's just like we jumped from 0.58 and 0.29 to these 4 decimals. I'm like, where is it coming from? And then the 15, it's just a lot of jumping. I'm sorry. It's, I was really following you. So,
Well, so back when I was over here, are you okay with these, with the square roots in there?
yeah, no, I remember that. I was good.
Okay, so then it's just a question of, how many, when I pop this into a calculator, if I'm just trying to teach the concept real quick, I said 0.58 and 0.29, just because having 4 decimal places would be like not that convenient for us.
Right.
But then when it was time to do angle bisector again, I felt like it would be better to actually go back to 0.5 over square root of 3 and
So just
type that into the calculator and
for
not
this
round.
particular polygon, which is a hexagon, right? You found it for this triangle, which is the 12th piece, right? Because there's 12 of these triangles, right triangles, in the hexagon
right.
itself, right? So you put
That's
that
right.
side, and then you're multiplying that side by 2 or by
Good.
12.
And then, wait, I'm multiplying it by 12 to get the perimeter, or
Of the-
by
of the
2 to
hexagon.
get. You're multiplying 0.2884 by 12, because here they are: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because this is only a piece of the right triangle.
Right?
The
That's the approximation for pi based on Archimedes' method. And then you did this again for
well, then once I have that these 3 sides, and you're right. I mean, when Scott says, the rounding, but of course I could have rounded any number of places. I kind of chose just round to nearest 10th just for the sake of instruction, because I think if I threw in 0.28845776, that would be a lot of decimals for the first iteration. But this is about 0.288 something and 0.57. I forget what they are.
and then
But once you have these 3 sides,
then you bisected this triangle again, which is a 30, 60, 90 triangle.
the original was, yeah.
Right? And then because with the bisector angle theorem, you're able to find that little piece.
That's right.
That's
right, because I know all 3 sides of this right triangle.
Right.
And if I know all 3 sides, I can do this, and that's where the 0.134 came from.
Right.
Okay. That I get.
But then, if you really wanted to go again, you'd have to figure out. But before you do that, you need the hypotenuse, because otherwise you wouldn't have all 3 sides of this lower triangle.
Now you got to do that. Okay, which is what we did earlier.
Yes. remember this question? 3, 4, bisector, bisector,
Right?
and we ended up with 0.71 here. It's almost the same thing, except instead of 3, 4, it's 0.5 and 0.5 over square root of 3. But otherwise, it's the same process. It's just with uglier numbers.
Right. Can I ask you to stop for just a second, because I'm trying, so I'm understanding the calculation now, but I've kind of lost the point. So how is all of this heavy duty calculation, how is Archimedes using this to prove pi or the value of pi? I guess that's what I've kind of lost in the process.
Because pi is also not just this ratio, but it's the circumference of the circle. Like it's actually pi inches in circumference. So
And
the
that's because,
hexagon is,
and that's because the radius is 0.5. That's true, right?
that's right. And
Okay.
this hexagon is bigger than the circle because the circle fits inside of it.
Right.
So its perimeter will be close to pi, but not exactly.
Okay.
And then the more sides I get, this 3.2 calculation that I got,
Yeah.
that is the actual perimeter of the 12-gon.
Gotcha.
And for the homework, how many iterations do you want us to do?
Let's take a look. I think we did 2. I think and we already did one of them, so I think there's 2 more to do. But let's see. We've already done question 1 and 2 and 3. No, we did 1 and 2. That's what we just did, but you should redo those. And then you'll do question 3, which is 1 more. I think you just got 1 more. No, you do 2 more iterations, 3 and 4. You could check your answers on that GeoGebra sketch. And then there's more questions for what I'm going to teach, now.
And this homework,
Okay, so that's our
homework is due Friday. 11 is due Friday, and 10 is due tomorrow.
So this one today, I mean, I was thinking 2 days for each homework, so today's Tuesday, so I meant to make it due on Thursday.
Thursday,
But that's
sorry.
all right.
No, I understand. Yeah, I meant Thursday.
Ken has some of those questions on it, by the way. I don't know if it was meant to be split or whatever.
There are
Like
there's a
homework
bunch
10
of questions,
that
although I'm
has
not.
at the bottom those 3 questions.
Oh, 3 more questions?
No, at the bottom of homework 10 are those 3 questions you just showed for homework 11.
That's right. Because we didn't get to them for homework 10. So I made them the first questions of homework 11.
He
Okay,
modified it.
Yeah, I changed it a bit. Okay, now I'm going to show you, all I'll have time for today in the last 15 minutes is some trisecting the angle. And as far as squaring the circle and doubling the cube, not going to do those today. Might do them tomorrow. So trisecting an angle is not possible with a compass and a straight edge. But it is possible if we are permitted to use some cheating. And the first cheating method is due to Archimedes. Let me explain what this is showing. Hold on. Actually, let me make it. So here is a circle and an angle. Pac-Man, random angle. Now, if you were to extend the diameter all the way, infinitely. Now, if you were to pick a point outside the circle on this ray, let's say I put it over here, and I were to join this point to this one, most likely this line segment right here, which I'm going to make purple, would not be the same length as the radius of the circle. Not same length as radius. In this case, it's way too short. If I were to pick a different point on that extended diameter, and I were to join it all the way to here, this line segment would be way bigger than the radius of the circle. This is smaller. This line segment is way bigger than the radius. Archimedes says in this picture here, which actually I have in on page 10, but I'm just going to talk this through because of time purposes. Archimedes says that if you can find the spot on the extended diameter, there's one perfect spot where FG would be the exact same length as CB. He says, if you can do it, there is a point, because every point either makes that line too small or too big, so there's some point that makes it just right. He says then, if this angle was 60 degrees, for instance, that this angle would be exactly 1/3. Now, finding this point is not possible with a compass and a straight edge, but this is still really clever. Let me convince you that he's not lying. Imagine I didn't know that it was 6. So again, the given information is that this is equal to this. Check it out. I think you'll like this. If I draw an auxiliary, can I call that angle X for now? Because that's like, we want to show that it's 20 degrees. If I draw an auxiliary line from here to here, this will be a radius also. Which means that this skinny triangle is isosceles, which means this is also X. Now, this angle out here would be 2x because of the exterior angle theorem. This is also a radius, so it's also equal to that line segment, which makes this triangle also an isosceles triangle, which puts a 2x. If 2x is one angle, base angle of the isosceles triangle, so is the other one. And now the sneakiest trick of all.
Isn't 2x
If
equal
I
to,
can-
isn't 2x equal to 60 because it's the
They're not parallel lines.
oh, right, only when it's parallel lines, right?
Now let's just look at this giant triangle. The 60 degrees is the exterior angle, and the two angles that it has to equal are this one and this one.
Yeah. Yes, that's true.
I'm going to, so imagine I just had 60 x and 2x. That's not an isosceles triangle. The green triangle, the big one, that when you put together the two triangles. So how slick of a use of the exterior angle theorem and the fact that the base angles of an isosceles triangle are congruent. That's ingenious. So you might say, wow, Archimedes did trisect the angle. But the problem is this point here, the perfect point that would cause, if you connected this point to the top corner, would cause this length to be equal to the radius. You can't find it with a compass and a straight edge. So it actually does not, it doesn't count. Still clever. And that becomes a new like research thing. Like maybe there's some way to get this point without worrying about whether it's a trisecting. So this is real slick, and I wanted to show you that one.
I don't understand why,
Archimedes.
wait, go back to that
Yeah.
picture for a second.
Yes.
Why can't you find that with a compass and a straight edge? Because it's the same radius, right? So you could just draw another circle and draw the diameter out and you would get F.
Well, we don't know this. So you're saying go from this point and make a circle? Because we don't know that point either.
Oh,
We don't know this point either.
oh, okay. That
Yeah,
makes-
it feels like it's possible. But remember, this must be one continuous, straight line, and it just can't be done. I know what you're saying. We know how big it has to be, but there's just no way to do it with a compass and a straight edge because we don't know this point either. So they would use another tool, like a ruler that's got a marking on it, because that was not allowed. But a what's called a marked ruler, you could do it then. You can only approximate it though. You kind of like take a ruler and kind of like you could get this pretty accurate with like a ruler that's got a marking on it.
Yes, professor, question.
Yes.
We said that this angle should be 30 degrees, but in this case, we prove that this is 20 degrees.
30 degrees?
Yeah, it is.
Yeah.
30. It's 30.
What's 30?
Well, because the supplement to 60 is 120, right?
Yeah.
Okay, you want to go like that? 120, yeah. So x plus
No,
2x.
it is. It is 20 because then you got 60. 60 divided by 3x is 20. No, it works.
Yeah. Very slick. Now,
I'm sorry,
Archimedes.
one more question. So
Yes.
I'm a little unclear from the picture. Where is the angle that we trisected?
This one. The central angle in the circle. So actually you can come over here. Here, you might like it better when you see it on dynamically. Hold on. Oh. If I come back over here and say Greek geometry. I must have it
Is
in
it
here. Let's
the
see. Archimedes
definition?
angle trisection. Here, I should have shown you this from the beginning. Because this will let me change the angle also. It's going a little bit slow here. So you see, I can change the original angle, and you can see the picture change accordingly.
I see. So
Notice how F would, depending on where D is, it makes the angle different, and it also makes the point F weird. Why is F not seem to be moving?
So the angle F is always 1/3.
Oh,
central.
I see. Yeah, here's the central angle, DCB.
Yeah.
I see what I have here. My thing actually lets you mess around with F and move it. And I have here the distance of FG is 4.93, but the radius is 2.61. So I move this until FG turns into 2.61, at least as close as I can. And then you can see the ratio between the two angles is 3. Whereas if F was somewhere else, this see this H? That H should be 3 when it's trisected. So it's not 3 because F is not at the perfect place because FG is too big. And over here, FG is too small. But if I move it so that FG is exactly or as close as I can get to 2.61, you will see that the angle is trisected.
Okay, so when we say trisect an angle, we don't mean that we have to actually cut the angle into 3 pieces. We'll just
That's right. That's right. Just
that's a third
produce.
of it. Okay,
Yes.
got it. Thank
Once
you.
you have that, yeah. Once you have that, you could copy this angle onto here because that's one of the things, but you wouldn't need to.
Thank you.
I'm going to finish with one last thing. No, actually, I'm going to call it quits for today. I am going to continue this lesson tomorrow. I'll cut. The problem was that we lost a full day on that Monday, and I never made it back. So I don't see us making up that day. So I just won't cover every possible thing, which just makes it easier for everybody, less to study for the final. More on the problems of antiquity tomorrow, and then jumping ahead thousands of years to the more modern history.
Time travel.
Yes. Okay, so I'll see everybody. Oh, and this also means that the homework will just go up until question 5. So I'll just say stop at question 5.
So homework 1 through 5.
Yeah. Weird, it's not letting me edit that just yet, but I will. Okay, we'll continue with this lesson tomorrow because we still have, 5, 6, 7, how many questions? A lot. So it'll probably take the whole class to just complete this lesson, and that's all right. I'll just shortchange the modern people a little bit. Okay, I'll see everyone tomorrow. And I'm sticking around right now if anyone has any questions.
Thank you, Professor. See you tomorrow.
Okay, see you tomorrow.